Dear students, welcome to all of you. Now we discuss about 2022 Unit-1 Mathematical Modeling paper DSE-A 2.2 Semester 6 B.Sc Honors in Mathematics, University of Calcutta. Question paper 2022 is Unit 1, Group B, Unit 1. Question 2, answer 1A. Obtain the Laplace transform of t square e to the power t sine 4t. Now, we use here L of ft equal to capital Fs. Now, L of sine at equal to a by a square plus a square. A is greater than 0. Therefore, L sine 4t equal to 4 by a square plus 4 square equal to 4 by a square plus 16. And now, L of e to the power at into ft is equal to f of s minus a. It is the first shifting property. So, L e to the power t sine 4t is equal to 4 by s minus 1 whole square plus 16. Now, L of t to the power n ft is equal to minus 1 to the power n dn dsn fs. So, L of t square e to the power t sine 4t equal to minus 1 square, second derivative with respect to s, 4 by s minus 1 whole square plus 16. Now, we simplify, this first derivative is this and second derivative is this. Check it, this. Next question, question 2a2. So that Bessel function j half x whole square plus j minus half x whole square equal to 2 by pi x. J in x is the Bessel function of first kind of order n. We know this j in x is equal to x to the power n, 2 to the power n gamma n plus 1, bracket 1 minus x square divided by 2 into 2 bracket n plus 1 plus x to the power 4 whole divided by 2 into 4 into 2 square into bracket n plus 1 into bracket n plus 2 minus and so on. Substituting this n equal to half in 1, we get this j half x, this equals to n equal to half. So we get this and this gamma half plus 1, so gamma 3 by 2. So this is root 2 root x, and this gamma 3 by 2 means half gamma half. This gamma half equal root pi. So after simplification, we get this is the whole root over 2 by pi x into sine x, because this is the series, this is the series expansion, this sine x. Next, substituting n equal to minus half in 1, and we get this series, and after simplification we get this equal to square root of 2 by pi x into cos x. This is the series of pi cos x. This sin x is this, cos x is this, and squaring and adding 2 and 3, we get this square plus j minus half x whole square equal to this root over of 2 pi x whole square sin square x plus cos square x, that is 2 by pi x is the result proof. Next question, question 2b1. If Pnx is the Legendre polynomial of degree n, and prove that x Pnx equal to 1 by 2n plus 1 bracket n plus 1 into Pn plus 1x plus n Pn minus 1x. From the generating function, we get 1 minus 2xz plus z square whole to the power minus half equal to series summation n equal to 0 to infinity z to the power n Pnx. Both sides, differentiating both sides of 1 with respect to z, we get minus half bracket 1 minus twice xz plus z square whole to the power minus 3 by 2 into bracket minus 2x plus 2z is equal to summation n equal to infinity, n equal to 0 to infinity n z to the power n minus 1 Pnx. Multiplying both sides by 1 minus 2xz plus z square, and we get this. So we get this x minus z, and this summation by 1, and this half equal to this summation z n z to the power n pnx. So this equal to summation z to the power n pnx, and this equal to this. So obviously multiplying this x into this, so this summation depends on n, so x into summation of this minus z, so z to the power n plus 1 summation pnx this equal to n into this, and after simplifying with this, equating coefficients of z to the power n from both sides, we get this z to the power n. So x pnx minus p n minus 1x, because this z to the power n plus 1, so z to the power n, and put here n equal to n minus 1, so here p n minus 1 here, so put here z to the power n, so put here n plus 1, so we get n plus 1 p n plus 1x, and this is the z to the power n, so 2xn pnx minus this plus this n z to the power n plus 1, so put here n minus 1, so n minus 1 into pn minus 1x, and after simplifying we get n plus 1 pn plus 1x equal to 2 n plus 1 bracket x into pnx minus n pn minus 1x, and this is another result for now from 3 after simplifying we get x pnx equal to n plus 1 pn plus 1x plus n into pn minus 1x whole divided by 2n plus 1. This is our result. Next question 2b2. Using Laplace transforms of the differential equation d2x dt square plus 9x equal to cos 2t with the initial condition this t equal to 0 and boundary condition t equal to pi by 2 equal to minus 1 t equal to 0 equal to 1 x at the point 0. So given differential equation is this, taking Laplace transform of both sides of 1, we get this L of d2 dt square plus 9 L of x plus equal to s by s square plus 2 square. This, so L of this d2 is dt square equal to s square lx minus s x0 minus x dash 0 plus 9 lx equal to s by s square plus 4. Now this set here this square lx equal to x bar, set here lx equal to x bar, so this lx equal to x bar, so a square plus 9 x bar minus s, because x0 equal to 1 is given, and x dash equals to c, say this x dash is c, x dash 0 equal to c, so value of x bar, that is Laplace transform by x, is equal to s plus c by s square plus 9 plus s by s square plus 4 into s square plus 9. And after simplifying, we get this. Taking inverse Laplace transform, we get this xt equal to L inverse of s by s square plus t square plus c by 3 L inverse 3 by s square plus t square plus 1 by 5 L inverse s by s square plus 2 square minus 1 by 5 L inverse s by s square plus 3 square. So it is equal to cos 3t plus c by 3 sin 3t plus 1 by 5 bracket cos 2t minus cos 3t, because L inverse s by s square plus s square equal to cos 80 and L inverse a by s square plus s square equal to sin 80. Hence, the result is this xt equal to 4 by 5 cos 3t plus c by 3 sin 3t plus 1 by 5 cos 2t. Call it equation 2. Now, it is given that x pi by 2 equal to minus 1. So, x pi by 2 equal to minus 1, put here t equal to pi by 2 in 2. So, we get this cos 3 pi by 2 equal to 0, and sin 3 pi by 2 equal to minus 1, and cos pi equal to minus 1. So, we get this, simplifying this c equal to 12 by 5. So, from 2, put here the value of c, this 12 by 5. C equal to the 5, so this is equal to 4 by 5 cos 3t plus 4 by 5 sin 3t plus 1 by 5 cos 2t. This is the required solution. Next question, question 2c. For each of the following differential equations, locate and classify its singular points on the x-axis. This 1 and this 2. Now, for this first differential equation, we write this y double dash minus 2 by x cube y plus 3 by x square into x minus 1 into y. Comparing with the standard form, this y double dash plus px y dash plus qxy equal to 0. And comparing, we get px equal to minus 2 by x cube, and 3 equal to q equal to 3 by x square into x minus 1. Now px is not differentiable at x equal to 0, and qx is not differentiable at x equal to 0 and x equal to 1. Hence there are two singular points, x equal to 0 and x equal to 1. Now to check this whether this x equal to 0, uh, whether it is irregular or irregular singular point. So limit x tends to 0 x minus 0 px. So this x tends to 0 x minus 1 by 2x cubed. So we get this limit tends to minus infinity. So x equal to 0 is an irregular singular point of the differential equation 1. Um, Next, to check at the point x equal to 1, irregular, limit x tends to 1, x minus 1 px, this equal to 0, and limit x tends to 1, x minus 1 whole square qx, this also equal to 0. So both limits exist finitely, so x equal to 1 is a regular singular point. Next, second differential equation in standard form is this. Equation 2, comparing, we get px equal to 1 by x into x plus 1 and px equal to 2 by x square into x square minus 1. Clearly, x equal to 0, x equal to 1, and x equal to minus 1 are three singular points of this differential equation. And check for x equal to 0, limit x tends to 0 x px, this equal to 1, limit x tends to 0 x square qx, this equal to 0. So both limits exist finitely. So this x equal to 0 is a regular singular point. And for x equal to 1, limit x tends to 1, x minus 1 into px, this equal to 0, limit x tends to 1, x minus 1 whole square qx, this equal to also 0. Hence x equal to 1 is also a regular singular point of the differential equation. And for check x equal to minus 1, limit x tends to minus 1, x minus minus 1 px, this equal to minus 1, limit x tends to minus 1, x minus minus 1 whole square qx, this equal to 0. So x equal to minus 1 is also a regular singular point of the differential equation 2. Next question, question 2D1. If Jnx is Bessel function of first kind and n belongs to the set of integers z, then show that j minus nx equal to minus 1 to the power n Jnx. Case 1, let n be a positive integer. Then j minus nx is equal to summation r equal to 0 to infinity minus 1 to the power r, 1 by r factorial gamma r minus n plus 1 x by 2 whole to the power minus n plus twice r. The definition of the Bessel function. Now we can split up this summation r equal to 0 to n minus 1 and r equal to n to infinity. And this equal to 0 because when r equal to 0, so this 1 minus n, and this for r equal to 0 to n, this negative gamma of negative integer, so obviously this infinity. This term, this summation, this series, this finite terms, this 0, and the remaining term part is this r equal to n to infinity minus 1 to the power r x by 2 whole to the power minus n plus twice r factorial gamma minus n plus r plus 1. Put r equal to n plus k. So k equal to 0. So r equal to n. So put r equal to n. So put when r equal to n, so k equal to 0. So put here r equal to k plus n. This we get this summation k equal to 0 to infinity minus 1 to the power k plus n x by 2 whole to the power n plus twice k whole divided by n plus k factorial gamma k plus 1. And so we get this summation. This depends on k. So minus 1 to the power n outside of this summation. This minus 1 to the power k x by 2 whole to the power n plus twice k. And gamma k plus 1 is k factorial. So put here gamma plus k plus 1 is k factorial. This minus 1 to the power k, and this k factorial. Now n plus k factorial equal to gamma n plus k plus 1 is n plus k factorial. So I can put this gamma n plus k plus 1 this, for this n plus k factorial. And this is the definition of Jnx. So for n positive integers, we get j minus nx equal to minus 1 to the power n Jnx. Case 2, if n be a negative integer, let n equal to minus p and p is greater than 0. So j of minus px equal to minus 1 to the power p j px. Because this p is positive. So from 1, we can put p is positive integer. So put here in p in place of n, we get this. So obviously jpx equals to 1 by minus 1 to the power p j minus px. So minus 1 to the power minus p j minus px. Now minus p equal to n, put here p equal to minus n. So we get this result. When n equal to 0, obviously this equal to j0x holds both sides equal this. And combining all these cases, we get j minus nx equal to minus 1 to the power n and j nx for n belongs to set of all integers. Next question, question D2. If Pnx is the Legendre polynomial of first kind of degree n, then so that integration minus 1 to 1 Pnx Pmx dx equals to 0 when n not equal to m. Let m not equal to n. Now, the Legendre polynomial Pnx is a solution of the Legendre equation bracket 1 minus x square into y double dash minus twice xy dash plus n into n plus 1 bracket y equal to 0. Then 1 minus x square, this pn double dash x minus twice in pn dash x plus n into n plus 1 pnx. This because this pnx is a solution of this differential equation. So this pnx satisfies this differential equation. So we can write this ddx of bracket 1 minus x square into pn dash x plus n into n plus 1 pnx equal to 0. Similarly, we can find for the Legendre polynomial pmx. So similarly, we can get the result 2. Now multiplying 1 by pmx minus multiplying 2 by pnx, we get this pmx ddx of this plus n into n plus 1 pnx and pmx minus pnx ddx of this minus m into n plus 1 pnx equal to 0. So combining, we get this ddx of 1 minus x square pmx into pn dash x minus pnx into pm dash x is equal to m minus n bracket into bracket m plus n plus 1 pmx into pnx. Integrating both sides from x equal to minus 1 to x equal to 1, we get integration minus 1 to 1 and d of this p m this 1 minus x squared this equal to integration m minus n into bracket n plus 1 pmx dx. Now this part is 0 and this put here when x equal to 1, this 1 minus 1 0 and the minus 1 is also 1 minus 1 equal to 0. So left hand side is equal to 0. Hence this this m minus n not equal to m. So m minus n not equal to 0. So we get minus 1 to 1 integration pmx dx equals to 0. And this completes the unit 1. Thank you for watching this video.